This video is for Chemistry in the Earth System, Unit 2.3, Electron Representations. Today's essential question is, how is an orbital diagram created? First main idea, visualizing electron configurations. When creating electron configurations, consider that the 1s orbital is always filled with electrons before the 2s orbital, which is always filled before the 2p orbital. This sequence is followed because the 1s orbital has less energy than the 2s orbital, which in turn has less energy than the 2p orbitals, and so on. In atoms that have electrons in more than 2 energy levels, the order in which orbitals are filled is more complex, and in these cases, an orbital diagram is helpful. An orbital diagram shows the orbitals used in a particular atom and the orbital's relative energies. Usually, empty squares are used to indicate the orbitals, and these squares are arranged to determine which orbitals are at higher energy levels than others. The closer an orbital is to the atomic nucleus, the lower its energy. The 1s orbital is closest to the nucleus and has the lowest energy. This energy level is always the first to be filled. Within an energy level, the higher azimuthal quantum number, the more energy in that orbital. The 2p orbitals, which have an azimuthal number of 1, are slightly higher in energy than the 2s orbitals, which have an azimuthal number of 0. The differences between the energy levels generally decrease further from the atomic nucleus. The energy gap between the 1s and 2s orbitals, for example, is larger than the gap between the 2s and the 3s orbitals. In some cases, the orbitals at an energy level further from the nucleus have lower energy than those in the next energy level down. For example, the 4s orbital has slightly lower energy than the 3d orbitals. In the case of potassium, the electron configuration is argon 4s1. In an orbital diagram for potassium, electrons are placed in the 4s orbital before they are placed in the 3d orbitals. Filling an orbital diagram. When filling an orbital diagram, remember the following rules. 1. The off-bow principle. The off-bow principle states that you must fill the lowest energy orbital that is available. Rule number 2. Hund's rule. Hund's rule states that you must place one arrow in each orbital of the same energy level before putting pairs of arrows in any orbital at that level. All the single electrons should be shown as having the same spin. In other words, all of the single arrows representing electrons in different orbitals at the same energy level should point up. Rule number 3, the Pauli exclusion principle. The Pauli exclusion principle states that if 2 electrons share an orbital, they must have opposite spins. No more than 2 electrons can share an orbital.
When atoms lose or gain electrons, they acquire a charge and become ions. The orbital diagrams for the ions reflect the addition or subtraction of the electron. For instance, here's the orbital diagram for the neutral element sodium again, and here's the orbital diagram for the positive sodium ion. The positive sodium ion has lost an electron, so its configuration is 1s2, 2s2, 2p6. When an atom loses an electron, it will always lose the electron from its outermost orbital. In the case of the neutral sodium, it lost the electron in the 3s orbital when it became an ion, because the 3s orbital is the outermost energy orbital that sodium was using.
So, orbitals are just pictures of where the electrons are and what they're doing in an atom. Electrons will fill orbitals in a fixed pattern, starting with the lower energy orbitals closest to the nucleus, then moving up and out from there. And by now, you're probably wondering Who the heck cares where the stupid electrons are? Well, aside from the fact that you'll be tested on it, you need to know where the electrons are in an atom because the positions of the electrons affect how the atoms come together, or bond, to form molecules.
The word orbital refers to the general region in an atom where an electron exists. An electron's orbital describes its average distance from the nucleus of an atom, what shape its possible path forms, or distribution, and how that distribution is oriented in space. In other words, where it is in relation to the atom's nucleus and other orbitals. Electron orbitals are described using three quantum numbers. The first, or principal quantum number, is represented by lowercase n, and it describes how far the electron is from the nucleus of the atom. The second quantum number is represented by a lowercase l, and describes the shape formed by the electron distribution, or the shape of the possible path an electron can take. Finally, m sub l, the magnetic quantum number, describes where the orbital is in relation to the nucleus and the other orbitals. A group of orbitals with the same principal number, or n, make up what's called an electron shell. Orbitals that have the same n and l values form what's called a subshell. Each orbital can hold a maximum of 2 electrons. An element's electrons will fill the lowest energy orbital first, then the higher levels. You can look once again to the periodic table to tell you the order in which the elements fill their atomic orbitals. By using orbital diagrams to represent electron configurations, it's easier to visualize how electrons are distributed among the atom's orbitals.
At this point, you should be able to generate a full and appropriate response to today's essential question. How is an orbital diagram created?